Hi, in this video, I'm going to continue on the industrial chemistry, and here I will be talking about experiments to determine the rate equation. Now, rate equation involving the order of reactants. So in order to write down or deduce the rate equation, we must find out the order with respect to each reactant. However, the order of reactants must be experimentally determined. So that's why we need to learn how to improvise experiment to determine the order with respect to each reactant. Now, down here, when we are improvising experiment, our objective is to change the concentration of reactant, and we also want to measure the initial rate for each concentration. Now, down here, A and B basically are the two important parts that we have to consider when we are designing or setting up experiments. Now, first of all, every time we study one reactant at a time. So, if the reaction is involving 3 reactants, then we need to have 3 series of experiments. Okay? So for example, this reaction A plus B forming C. First of all, we target on reactant A, and we want to see how the concentration of A affects the rate, or in other words, we want to find out the order with respect to A. So in order to do that, we will perform the experiment either by changing the concentration of A while keeping the concentration of B the same, or a similar way is to change the concentration of A while using large excess of B. Now, when you use large excess of B, when the reaction proceeds, the concentration of B does not change, or more or less doesn't change, because it is large excess, right? So, no matter you do 1 or 2, you are basically using the same concentration of B. So we set the concentration of B as the controlled variables, and every time we are changing the concentration of A. And for each trial, we are looking at the initial rate. So then we are able to establish the relationship between the concentration of A and the initial rate, and from there we are able to tell the order with respect to A. Okay? Now, down here, you notice that we are not measuring average rate, we are not measuring instantaneous rate, but we are particularly interested at the initial rate. But why are we so interested at the initial rate? Here, the reason why we are interested in studying the initial rate is that for initial rate, we know the concentration of reactant. Okay? However, if you're studying any rate other than initial rate, we have no idea what the concentration of the reactant is. After all, we want to establish a series of data consisting of rate and the corresponding concentration. Now, here, initial rates can be obtained by drawing a tangent to the concentration time graph when time equals to 0. And this one, I will show you how it works by using the case study 1. But this is one way of doing it. The second method is we want to find out how long it takes for the reaction to produce small but fixed amount of one of the products. Okay? And this one can be illustrated by looking at case study 2 and 3. Okay? Now, I'm not going to give you general steps. Instead, I will give you 3 case studies. So from there, you are able to get how we can design or how we can carry out experiments to determine the rate equation of a reaction. So let's get started by looking at the first example. The first example consists of the decomposition of hydrogen peroxide by a biological catalyst called catalase. Okay, it is a catalyst. Now, the equation you see, hydrogen peroxide decomposed to form O2 and H2, and the reaction can be monitored by recording the volume of oxygen produced at different time. Okay, so we can record the volume of gas using this inverted burette, okay? Or you can use a syringe. Now, down here, you see, we use different initial concentration of hydrogen peroxide, and we register 5 different curves. And from these 5 different curves, we can find out the tangent to the curve when time equals to 0. That one will give us the initial rate. So that's why we can have initial rate 1, 2, 3, 4, 5 corresponding to the initial concentration. Now, after we have collected these data, we are able to plot a rate concentration graph. Okay? And you notice that this rate concentration graph is a straight line passing through origin. So you can tell the rate is directly proportional to the concentration of hydrogen peroxide. Therefore, we can conclude that it is first order with respect to hydrogen peroxide. Okay? So it looks easy, but you can tell when you actually have to perform this experiment, it's quite tedious. At least this experiment you have to perform like 5 times. And each trial, you need to record several data in order to construct a reliable curve. Okay? Now down here, simply asking you, how do we find out the order of reaction with respect to catalase? Even though catalase is not a reactant, still, catalase participate in the reaction. And obviously, catalase affects the rate of reaction. So the catalyst itself may also have an order. So here, we also have to pay attention to the order with respect to catalase. Now, but here, if you want to modify this experiment so that we are able to determine the order with respect to catalase, we can simply fix the concentration of hydrogen peroxide, and then we add different concentration of catalase. Okay, so here we can simply keep concentration of H2O2 constant, vary the catalase concentration, and repeat experiment. Okay, so this is how it works. Okay, so this method we construct several concentration time graph. Now, the volume of O2 is actually used to represent the concentration of the product, so it is also considered as a concentration time graph. So this one, we construct several concentration time graph using different concentration of the hydrogen peroxide, the reactant, and then from there we find the initial rate, and using the initial rate and the corresponding concentration, we construct a rate concentration graph, and from there we are able to deduce the order. Now this method works, but not very useful. Very often we go for the second method. Okay, let's have a look at this one. Now, case study 2. So here, we want to study the reaction between sodium thiosulfate and sulfuric acid. Actually, this reaction, we have talked about it when we talk about the rate of reaction. Okay, so you see, sodium thiosulfate solution reacts with dilute sulfuric acid solution to give you a bunch of products, but the key is, of course, the sulfur solid. Now, the production of elemental sulfur is the key as to how or why the solution becomes so opaque, because sulfur is insoluble in water. Now, what we're going to do is, we're going to have, again, a cross at the bottom, put a beaker containing perhaps the thiosulfate solution, and then we pour in the sulfuric acid, start the timer, and then we want to measure the time it takes to mask the cross. The time it takes to mask the cross indicates that a certain quantity of sulfur has been produced. So you can tell if it takes a shorter time to have the cross being masked away, that means it takes a shorter time to produce a fixed amount of sulfur. That means the reaction is fast. Okay? Now, so the time it takes for the reaction to complete, by complete that means the cross being masked, the time it takes for the reaction to complete is inversely proportional to the rate, because the shorter the time it takes, the faster the rate. So we use 1 over T, down here you can see, we use 1 over T to represent the rate. Okay? So for each experiment, we can change the concentration of one reactant while keeping the others constant. Then we can repeat these experiments several times to register several initial rate with several corresponding concentration of the reactant, and again we will plot a rate concentration graph, and then after that we find out the order with respect to that reactant. Repeat that experiment again with another reactant, then again we will register the order with respect to the other reactant, and after that we are able to establish the rate equation. Okay? Now you can see this table down here. So I did 6 trials, and you see these trials I used the same volume of 0.5 sulfuric acid. That means the concentration of sulfuric acid is constant. Now here we are changing the volume of sodium thiosulfate. So you can tell the more sodium thiosulfate I use, the higher the concentration of sodium thiosulfate. Now you also notice that I add water, and the volume of water added depends on the volume of thiosulfate added. Basically, we want these two altogether added together being 30 cm cube. Or you can say the overall mixture is 50 cm cube. Okay? The reason why we add water to make the volume the same every time is because we want to have the volume of sodium thiosulfate added being directly proportional to its concentration. Okay? Also, the volume of liquid would also affect how much sulfur it needs to make the solution opaque enough to mask the cross. Okay? So that's why we have to add water, even though water is not a reactant. Okay? Now you see, with different concentration of thiosulfate, it takes different quantity of time to make the solution opaque, and we're taking a reciprocal of this time, we register a bunch of rates of reaction, and you can tell with the highest concentration of sodium thiosulfate, it registers the fastest rate. Okay? Now, so we are using basically this information together with this information. Okay? We are going to establish a rate concentration graph. And you see, rate concentration graph, even though it is volume, actually it is representing the concentration. Now you see, we register straight line passing through origin. What does it tell you? Well, it tells you that it is first order with respect to sodium thiosulfate. Okay? So first order with respect to sodium thiosulfate. Okay? But down here, this is what I just mentioned about the purpose of adding water. So different volumes of water are added. So to make the total volume of the solutions the same. Okay? This way, the concentration of sodium thiosulfate in each trial is proportional to the volume of sodium thiosulfate added. Okay? Which makes a more easy comparison. Okay? So that would be the second experiment. And you notice that this time we don't have to construct like 5 concentration time graphs. Here we simply have to perform like a few trials, okay? And then we register the time. Of course, you will make repeated trials for each concentration for better precision. That's up to you. But at least this is the least number of trials you have to do, like 6, maybe 5, okay? Now, case 3, iodine clock reaction. So this is a new type of reaction, so probably you have to pay attention to it. Now, iodine clock experiment. First of all, a clock experiment or clock reaction, you know a clock will ring when time strikes to the point you set up. For example, you have set it, the clock to ring at 6 a.m. in the morning, and now it is like 5 a.m. in the morning, so it takes 1 hour for the clock to ring. Otherwise, the clock doesn't ring at all. Okay, so you notice that this clock reaction, similar to a clock, which doesn't give you any sound until the time comes. When the time comes, it rings very strongly, very loudly, and you see a very distinctive observation. And this is the feature of clock experiment. Gives you nothing at the beginning until the time reach, and when the time reach, it gives you a very distinctive observation. Okay. Now you see, a significant observation can be seen at a particular time after the reaction is starting. Okay. Now, in the iodine clock reaction, we have 3 reactants and 1 indicator. We have this peroxyl disulfide ion, we have iodide ion, and thiosulfate ion. The indicator, we use starch solution. Now, all of these solutions are colorless. Okay. Now, the main reaction involved in the clock experiment is this one. Okay, where peroxyl disulfide ion reacts with iodide to form sulfate and iodine. Okay. Now, this reaction is not very fast, knowing that we have negative ions colliding each other, so the repulsion makes it more difficult. Now, you notice that this reaction produces iodine. Now, when you see iodine and when you see the starch solution, you may think, it gives you a blue-black complex, isn't it? Blue-black complex. But it is not the case, because the iodine produced it before it can reach the starch molecules, it will actually react with the thiosulfate. And the thiosulfate is able to convert the iodine back to iodine. Okay? Basically, the thiosulfate removes the iodine produced it. Okay? Now, in this clock experiment, we will add, again, small but fixed amount of thiosulfate ions. Okay? So, this thiosulfate ion will consume iodine made from the main reaction. So you think about it. In order to bring about a color change, you must produce enough iodine so that it can completely consume all these thiosulfate. So when the moment where all the thiosulfate is consumed, any extra iodine produced from the main reaction will combine with the starch molecule, giving you the blue-black color. Okay? So that's why your reaction mixture is colorless at the beginning. Even when everything is mixed, it is still colorless. And when the time comes to the point where all the thiosulfate is consumed, any additional iodine produced from the main reaction combines with the starch, giving you a blue-black color. Okay, and this is the time where you need to stop your stopwatch and record the time it takes for the color change. Okay, so you see, when all the thiosulfate are consumed, any additional iodine produced will immediately form a dark blue complex. Okay, now what is the purpose of thiosulfate then? Well, besides dilating the reaction to give you that dramatic observation, actually, this thiosulfate is used to indicate a certain amount of iodine being produced. So here, we want to record the time it takes for a certain quantity of iodine to be produced from the main reaction. Okay? So down here, you can tell if the reaction goes faster, it produces iodine faster, so it takes a shorter time to consume all the thiosulfate and brings about the color change, then you can tell the reaction should be faster. Okay, so that's why the time it takes is inversely proportional to the rate. So the rate can be expressed by 1 over T. Okay, the T is the time it takes for the dark blue color to appear. Okay, so this one is actually similar to just now the thiosulfate with the cross being masked by the solution. Again, we want to measure the time it takes for a small but fixed amount of reactant being produced. Okay? So these are the 3 case studies. So probably you have some idea in your mind how you can design experiments and how you can record useful data and at the end deduce the order of reaction. Now this part, what we try to do is, now we are given with experimental data and we want to make use of this data to deduce the order of reaction. Okay? Now, let's just say we have a reaction A plus B plus C forming D and E. Okay, so you can tell we need to perform three series of reaction to find out the order with respect to A, B, C. Okay, now down here it has performed several experiments and it has also recorded the concentration of each reactant. Okay, now we use initial concentration and we measure the initial rate because, like I said, initial rate we know the corresponding concentration, right? Now you notice that if you look at experiment 1 and 2, so the concentration of B and C are both 1, so they are the same. The only difference is the concentration of A, which has been doubled. Now remember, every time we only change one variables. So when you compare experiment 1 and 2, the only changes is the concentration of A, which is doubled. Then you look at the initial rate. You notice that A, it is also doubled. What does it tell you about the order with respect to A? Well, of course, it is first order. Okay? This is actually what I did down here. Okay? Comparing experiment 1 and 2, doubling of concentration of A results in doubling of initial rate. Therefore, the order with respect to A is 1. Okay? So this is how we can make use of the experimental data to make deduction. Okay, now, what do we do next? We want to look at B. Let's just say we want to look at B. Now, it's up to you which set of data or which experiments you compare. But of course, like I said, you need to find something that has one change only. Okay? So in this case, I will compare 1 and 3. Because 1 and 3, you notice that the concentration of A and C are the same, and the only change is the B. Okay? So you notice that from here to here, again, 2 times increase in concentration, and this results in 4 times increase in rate. 4 times increase in rate. So what does it tell you about the order? Well, doubling of B results in quadrupling of initial rate, so the order with respect to B is 2. Okay, so this is the second deduction. Now the third deduction, of course, what we have left is C. So we can compare experiment 1 and 4. Knowing that doubling the concentration of C resulting in no change in rate. Okay, doubling concentration of C resulting in no change in rate. So what does it tell you? Well, it tells you that it is 0 order with respect to C. Okay, so this is the third deduction. Doubling of C results in no change in initial rates, therefore the order with respect to C is 0. Okay, so this is the first method, how we can deduce the order from the experimental result. This one is quite simple. Okay, I recommend this one if this is if it works. But sometimes it doesn't work that easy because sometimes the order is not that easy to tell, especially like the experimental results, they are not necessarily 2 times, 4 times. Sometimes it could be 1.5 times, sometimes it could be 0.75 times. So it will be a little bit difficult to simply look at it and write down the deduction. Sometimes calculation is more reliable. Okay. Now, so that's why I will also introduce method 2, which is to determine the order by using the method of calculation, basically simultaneous equation. So, first of all, we will establish hypothetical equation by plugging in the concentrations for each experiment. Okay. Now, and then we will compare each 2. Then we will compare equations, okay, 1 by 1. By doing this, we will have 2 divided by 1. Let's just say we do 2 divided by 1. So you see 1 to the power y can be cancelled out. 1 to the power z can be cancelled out. So what we have left, k can also be cancelled out. So we have 0.04 divided by 0.02 equals to 2 to the power x divided by 1 to the power x. Okay? So in this case, x must be equals to 1, and therefore it is first order with respect to A. Similarly, we do 3 over 1, 4 over 1, and we can calculate the order with respect to each reactant. Now this one may look more tedious, but I would say this method is more versatile. In many situations, in most situations, we can use this method. Okay? This method is only useful when the data is easy to comprehend. Okay? So my suggestion is, if the question provides you good numbers, easy to handle, you go for this method. If the numbers is a little bit kinky, you go for this one. Okay? Now, down here, so from all this deduction, the rate equation is rate equals to K times A to the power 1, but the 1 we don't show it, times concentration of B squared. So the overall order of reaction is 3. Okay? Now, we can also calculate the value of K, the rate constant, after we establish the rate equation. Simply, you use any set of data, you plug it into the equation, tap the calculator, you can find out the K. You can also write down the unit of the K. Okay? So, this one is a very popular type of question in DSE, so you must know how to do this, and to be honest, it's not difficult. Now at the back, we have practice question. So I will do one, and then you will do the rest. Okay, I will try to use both methods. So for each method, it may take quite a lot of space, so it would be best if you write a little bit smaller. Here, we have a couple of things to do. Rate expression, order of reaction, rate constant. So 3 things. Now, first of all, here, I use the first method, so I want to compare trials. So, first of all, I want to compare, for example, the first one, okay? So, compare trial 1 and 2. You notice that this one has a change, but the rate, no change, isn't it? Right? So, we say that changing concentration of iodine has no effect on initial rate. So, it is 0 order with respect to I2. Okay? And then we can compare perhaps 1 and 3. 1 and 3. So you see, the concentration has increased by 2 times, and the initial rate has also increased by 2 times, right? So again, we can comparing trial 1 and 3. So doubling H plus concentration, okay, doubles the initial rate. So it is first order with respect to H plus. Now you notice that H plus is the catalyst, but it still has an order with respect to it. Now, the last one, we want to look at the ketone, the propanol. So I will be looking at the trial 1 and 4. You notice that this one, the concentration is half by 2. And the initial rate is also half by 2, right? So comparing trial 1 and 4, halving the propanol concentration halves the initial rate. Okay, so it is also first order with respect to iodine. Sorry, this is the propanol. Okay. All right. Now, so the equation, the overall equation. So rate equals to K H plus and the propanol. Okay, this is the overall equation, and the rate constant. So substitute data from trial 1. Okay, so we have 7.0 times 10 to the power negative 5 equals to times K. Equals to K times concentration of H plus 5 times 10 to the power negative 3, also multiplied by the concentration of ketone, which is 4 times 10 to the power negative 1. Then K equals to, you just tap your calculator. So you got 0.035. The unit is a second order reaction, so it would be dm cube mole negative 1. Okay? So this is how it works using the first method. Now for the second method, simply we use equations. So I'm not writing all those hypothetical equations. Again, I can compare trial 1 and 2. Okay. So when 2 divided by 1, we have 1 equals to, this is x, y, z. X, y, z. So here we will have 1.5 times 10 to the power negative 4 x over 2.5 times 10 to the power negative 4 x. Okay, now this one, x must be 0. Okay, x must be 0. It can't be any other numbers. So that's why it is zero order with respect to I2. Okay? Now, of course, like I said, this equation is not necessary, but I'm just write down once to illustrate to you how it works. Now we can do something similar. Okay. Alright, so I do not repeat myself with the K, and I don't repeat myself with the general rate equation. Okay. Now, you can spend some time working on B. Okay, you can spend some time working on B. You can use either one of the two methods, see which one is better. Okay, you should pause the video and try yourself, and resume the video and check the answers. Okay, let's have a look. Alright, I will use, let's see. Okay, I'll use the numerical method. So at the beginning, I should compare 1 and 2. Okay, so So the overall equation rate equals to K Br minus BrO3 minus and also H plus square. Okay. I will use one set of data. I will use so sub in data from trial 1. So we have the rate equals to K times 0.1, 0.1 squared. So K equals to basically divided by 0.1 to the power 4, isn't it? So we have 800, okay? Units, so the units, because altogether the overall order of reaction is 4, so this one should be dm9 mole to the power -3 s to the power -1, okay? Alright. It also requires the order of reaction. Let's just put down, okay, order of reaction is 4, okay? Because the order of reaction is the total, is the sum of order with respect to each reactant. So it's 1 plus 1 plus 4. Sorry, 1 plus 1 plus 2, okay? So that's that. Alright, I will stop the video here.